Now let's talk about turning logic equations into gates. So here we have an equation y equals a and b bar, or c bar, d, and e. And so we see that we have two product terms, and so we'll put down two AND gates, and then we'll put our inputs from the left, a and, well, we need to invert b bar. We need to invert C as well, so we'll put inverter there, C bar and D and E. So now we have our two product terms, our two implicants, and we'll now put our OR gate to OR those together and output Y. And so we can see that our inputs flow from the left to the right as well as our gates, and our output is on the right. And so we can implement any sum of products or SOP form of the equation using two-level logic with a level of AND gates followed by a level of OR gates. So some schematic rules, circuit schematic rules, are to put the inputs on the left or the top. So in this case, we have them on the left. Outputs are on the right or the bottom. I'll show an example of these two cases in a moment. And gates flow from the left to the right, and straight wires are best. So here's an example of the inputs coming from the top. So here we have A, B, bar, C, bar, D, and E. And now we can put our AND gates here, our product terms, our implicants, A and B bar, or C bar and D and E. And now we can put our OR gate. Could have put it on the right there too, but we can also put it on the bottom, where we grab our two implicants and output Y. And so this is useful if we're doing multiple outputs circuits. So for example, if we have another output here, W or something, and that's just the second output, W is just A and B bar. Or we could have another output. When we draw our schematics, we want to make sure that we use circuit schematic rules, including how we draw the wires. So wires always connect at a T junction. So here, this is a connection. There's a T junction, like that. Right, so wires connect there. Wires do not connect if they just cross over each other. That's what's shown in this picture. But if they cross over each other and there's a dot, then they do connect. So wires that cross with a dot are connected. Wires that cross without a dot are not connected. And circuit schematic rules, you'll see different schematics as you view more and more schematics. So some people do an extra. So for example, showing the no connection instead of just crossing, I'll show this little jog to indicate that it doesn't connect. That makes circuit schematics more cluttery, so we don't use that method in this class. So no connection is just shown by two wires crossing. If I want those two wires to connect, I need to add a dot. So again, two-level logic is ANDs followed by ORs, and this is useful for implementing SOP or sum of products, because we have our product terms, our AND terms, and our sum terms. And this can be used for minimized sum of products form or canonical sum of products form. This equation here is in canonical sum of products form, because each term, assuming y is a function of A, B, and C, because each implicant or product term and term includes some form of each of the input variables. And so we can implement that using two-level logic. And one thing I want to point out here is you can see that this regularity, this regular structure, A and A bar, B, and then we have B bar, C, and then we have C bar here, makes it easy to grab the variable or its complement because of its regular structure. And so when we make our product terms, we can just grab A bar and B bar and C bar. Makes it an easy, regular way to do that. And so if we're grabbing a bunch of, or making a bunch of product terms, that regular structure makes it really easy to both implement and then also debug. And so we have our product terms, our implicants here, our min terms in this case, and then we have our sum term being created by this OR gate, our OR term, creating the output Y. And if we wanted to use a minimal number of gates, we would have first needed to minimize that equation. So we can also use multi-level logic where we have more than two levels, and complex logic is often built from many stages of simpler gates. So for example, here's an example of an 8-input XOR gate. And it's completed by using 3 stages of XOR gates, of 2-input XOR gates. And here is another function using 3 stages. And so we can, often this more complex logic we're going to implement using multiple stages. So we can also have multiple outputs of our circuit. So instead of just multiple inputs, we can have multiple outputs. And here's an example called the priority circuit. The output's going to assert corresponding to the most significant true input. So here are inputs A3 to A0, and we could also write that. Right? We could write those inputs A3 colon 0. That's the same as, it's equivalent to A3, A2, A1, A0. It's just a more concise way to write that. And so let's suppose our inputs, the highest priority is A3. So let's suppose, for example, we have priority for people requesting to use an auditorium on campus. And so here's the president of the university, and he or she has the highest priority. And then maybe there's the college dean, and then there's the department chair, and then lowest priority is perhaps the faculty member. Okay, so we have these prioritized inputs, and if the president requests use of the auditorium, his or her output, Y3, is going to assert, saying, oh, yep, you get use of the room. Right, so if A3 requests it, Y3 is going to assert. So we look at our truth table here, showing all possible combinations of requests on A3 to A0. And whenever A3 requests the use of the auditorium, says, A3 equals 1, then Y3, the output, asserts, saying, yes, you get the use of the room, and no one else does. So then all the other outputs say 0, sorry. Even if you wanted to use the room, all of these ones requesting it, out of luck. Someone with higher priority requested the room. And so, when A3 equals 1, Y3 equals 1. But if A3 is 0, and the next highest priority input goes high, so in this case the dean says, oh, actually I'd like to use the auditorium. Doesn't matter what the lower priority inputs are, they happen to be requesting it in some cases. Still, well, so the president didn't want it, so there's a 0 there. Again, we can put our line here to keep alignment. But Y2 asserts to say, yeah, the dean gets it in that case, gets to use that room. and the lower priority outputs are 0. And then, the chair, if none of the higher priority inputs want to use the room and the department chair requests the room, the department chair gets to use the room, even if the faculty member requests it. And finally, if the faculty member requests the room and none of the higher priority inputs have requested it, then the faculty member's output is 1 to indicate, yep, you get to use the room. And finally, we also have to cover the case where no one is requesting the room. Well, then of course nobody gets to use the room because nobody wants to. And so again, we have the cases of the highest priority input requesting the room, the next highest priority input requesting the room without the highest priority input requesting the room, the next highest priority input requesting the room, and finally the lowest priority input requesting the room without any of the higher inputs requesting the room. And the final case of no one requesting the room. So now we can write equations for this priority circuit. And notice that we do now have 4 outputs, y3 to y0. And we could write that like this, y3 colon 0. We could also write it y3 colon 0, indicating there are 4 bits of this output. They have the same name, y, because they're associated. But we could have written this table as 4 separate tables. So, right, we could have written a table that just has y3 on the output, or we could have written a table that just has y2 on the output of the truth table, or y1, or y0. But it's a pain to write this, 4 times. And also, these outputs are related, so we're going to keep them on the same truth table, but we're going to treat them individually, right? Where we write an equation for y3 as if none of the other outputs are there, and then y2, y1, and y0. So we treat them individually. So let's first look at y3. So we look at where the 1s are, and we're going to say, okay, well, yeah, y3 is 1 whenever a3 is 1, and that's almost, from what we said in words, how the circuit works. But y3 equals a3. Cool, that makes sense. All right, let's look at y2. Well, y2 is 1 when a2 is 1. So we would be tempted maybe to write it just like this, y2 equals a2, but that would make it assert here as well, and we don't want that. So y2 equals a2, but preceded by a3 being false. So a3 has to be false, a3 bar, and a2. Now we can consider this column, the y1 output. y1 is going to be true, well, when a3 is not true, and a2 is not true, and a1 is true. And finally, our last output, y0. y0 equals, well, now we're just doing directly sum of products. There's only 1 in this output. y0 equals a3 bar, and a2 bar, and a1 bar, and a0. And so we read our outputs directly from this circuit, from this truth table. And then we can write equations for those, write circuits for those equations as well. So y3 would be pretty easy. We can grab it like this, i3, and then we could, so we need the true and complement version of all of them except a0, so we could do something like this, for example, where we have the true and complement version, a3 of a3, a2, a1, and a0, and we're going to say, okay, well, y3 equals a3. That one's pretty easy, so we say y3 equals a3. Got it. And now we're going to do y2 equals Well, it's going to be a 2-input AND gate, A3 bar and A2. Y1 is also an AND, just a product term or implicant, is A3 bar and A2 bar and A1. And finally, Y0 is A3 bar and A2 bar and A1 bar and A0. And you can see how this regular structure of our inputs, having the true and complement forms, makes it really quite easy to grab our inputs from in that circuit. And I wanted to show another way of doing this. So we just show the true form of A3, A2, A1, and A0 coming down, and then we can put bubbles on the inputs to indicate the inversion. And so we have A3 bar and A2, for example. So let's talk about don't cares. A don't care is indicated by the symbol X. So don't care means a 1 or a 0. So it doesn't mean it can be, kind of between 1 and 0 or some other value or not driven to a value. It means I don't care which it is. It could be a 1 or a 0, but not both. But it has to be, one of those. But I don't care which one it is. So we could include don't cares in our truth table to help clarify, actually helps kind of clarify what the meaning of the truth table is. So when A3 is 1, we don't really care what the other inputs are. So we can put don't cares there, because when A3 is 1, Y3 is 1, and all the other outputs are 0, independent of what these other values are, A2, A1, and A0. So these don't cares cover all these combinations, these in this case 8 combinations of the other inputs. Okay, and then we could do the same thing for the next 4 rows. Well, when A3 is 0 and A2 is 1, we don't care what the other inputs are. And the output would be 0, 1, 0, 0. And the next 2 rows, if A3 and A2 are 0 and A1 is 1, we don't care what A0 is, right? That covers these 2 cases. Then Y3 is 0, Y2 is 0, and only Y1 is 1. And finally, we have this row here, when A3, A2, A1, and A0 are 0, and A1 is 1, then Y0 should be 1, and all the other outputs should be 0. And then the final case, when all of the inputs are 0, all of the outputs should be 0 as well. And so by using don't cares in our truth table, it actually simplifies our truth table. It's a lot more concise, and it really makes it easy to see what the equations are. So we can see that Y3 equals A3, Y3 equals A3. Yeah, these aren't even included in our equation. Y2 equals, well, A3 bar and A2. Don't care what, we're not even looking at A1 and A0. Those don't even affect the output. Y1 equals A3 bar and A2 bar and A1. Don't include A0 in our equation. And Y0 equals A3 bar and A2 bar and A1 bar and A0. That's the only pure SOP, sum of products, that we've talked about before, form of the equation.